Okay, welcome after the break. And so our second speaker for today is Martina Rovelli, who will speak about more model structures on cubical sets of infinity categories and infinity groupoids.
Thank you, Chris.
In the moment.
Thanks. And I join you in wishing cubical set the brightest future after this working group. But as a disclaimer, I'm not an expert in this topic. I spent some time last year thinking about a few things and mostly on how to build model structures on cubical sets in a lazy way. And that's what I want to talk about today. Okay, so as any talk on cubical sets, the very first thing that we should agree on is what is the category of cubes that we will focus on for this talk. And I am picking one that Chris doesn't seem to like very much, which sometimes was referred to as the Dedekind cube category, or alternatively, this is also the full subcategory of the category cat spanned by the powers of the walking arrow. And if you prefer the description in terms of what maps generated, this is the one that is generated by faces, degeneracies, diagonals, and both connections. So this is essentially the largest that we have seen so far, but there is no reversals. And then once we have agreed that this is what we will be looking at today, then as usual, we are gonna say that the category of cubical sets is just the category of presheaves valued in sets indexed over this category that I have chosen. And there is a triangulation functor that will eat a cubical set and produce a simplicial set for us. And what I'm trying to accomplish is to use this triangulation to transfer the homotopy theory that is present in simplicial set to cubical sets. And what I'm saying can be read at the same time if you're thinking about homotopy theory of infinity groupoids or homotopy theory of infinity categories. So what are our two favorite model categories of simplicial set? We have the Canquillen model structure on one side and the Joyard model structure on the other side. And just to agree on a uniform notation, that's the way that I'm going to write them. Infinity 0 and infinity 1. And then I couldn't resist calling the general notation simplicial set infinity epsilon, since in this working group, epsilon clearly has values 0 and 1. And so for whatever I say, you can just fix one value of epsilon and you're gonna get two theorems, remarks, or whatever I'm saying for both situations. And in principle, one could even try and go more general, but these are really the two examples that probably make sense to have in mind. And I said that I want to transfer these model structures to cubical sets. And in the beginning, I was not aware that T also had a left adjoint. So I only knew that it had a right adjoint. So the thing that I had started playing with first was on constructing the left transferred model structure using the functor T. So what is this? This is a model structure on cubical sets in which T, the triangulation functor, creates cofibrations and weak equivalencies. And then in an email conversation with Christian Sattler, he also pointed out that, yeah, okay, that's the notation that I will use. I'm decorating cubical sets with an L because it's the left transferred, as opposed to the right transfer that is going to come in a moment. So as I was saying, Christian suggested that one could also do the right transfer model structure. And this is a model structure in which not cofibrations and weak equivalencies, but fibrations and weak equivalencies are created by T. And not only these model structures exist, but they also have the correct homotopy theory. So when you fix your favorite value of epsilon, then you're going to recover infinity groupoids and infinity categories. And the more precise statement to support the imprecise statement is to say that T is the left Quillen functor in a Quillen equivalence, if you're looking at the left side of the beamer. And it's also a right Quillen functor with respect to the blue model structure. So that's where we're gonna go, and we will see that the reason why I said that I was looking for the lazy way is that it's quite easy to accomplish, to show the existence of these two model structures and even to prove that the desired adjunctions are equivalent equivalencies. However, the price to pay is that these model structures are somehow artificial. They're not like fully using the intuition that we may have on cubical sets. So I imagine that if you're trying to prove something really deep about cubical sets, you may not be able to go very far with these model structures. But let's see, we will explore them a little bit and try to have a feel for what are their gadgets. Okay, so I said that the proof will be somehow formal. And what I mean by this is that essentially we just need a couple of ingredients, a couple of properties of the triangulation functor. So here I'm recalling for you once again that the triangulation functor takes a cubical set to a simplicial set. And if you forgot what it does, we don't really need it, but I just wanted to have some math on the slide. It takes the representable n cube to the n-fold product of the one simplex with itself. And then it's defined by taking like the continuous extension of whatever it does on representables. And the first feature that I will care about is that T actually fits into an adjoint triple. So for different choices of the cube category, can you see my cursor?
Yes.
Okay, so this part of the adjunction is present for any category of cubes, but for my specific choice of cubes, then you also get this extra character to the left. And yeah, so this is the triple of adjoint functors. And again, just for the sake of having a couple of formulas, I can tell you what the functors do. So the functor C, I'm calling it a cubification. I think Chris called it U at some point. And here's the explicit formula on what it does. It takes a simplicial set X, and then Cx is a cubical set, and the collection of n cubes is the collection of maps of simplicial sets from delta 1 to the n into X. And instead, the left adjoint, I'm calling it flat, and I can tell you what it does on representables. On representables, it does the same thing as the cubification. So maybe this in the beginning is counterintuitive, but the difference is that then it will also be extended co-continuously, which is not the case for the cubification, which is not a left adjoint. Okay, so I invite you to forget all of these formulas because we will not use them even once. And really all we care about is that the existence of this adjoint triple is buying a lot of formal properties for us. So we know for free that T will preserve all limits, co-limits, and monomorphisms. So that's what you should remember from this block. And yes, and the second part that we use is that both C and flat are fully faithful functors. They are embeddings. So this was mentioned in Chris' talk, I think, regarding what I call the cubification functor. He had described to us that the cubification could be seen as the inclusion of certain sheaves into the category of pre-sheaves. And it is a formal fact that when you have in an adjoint triple, if one of the two external functors is fully faithful, also the other one is fully faithful. So we're getting that also flat is an embedding. And again, what this means is that when you look at the unit of one adjunction and the co-unit of the other adjunction, then these are going to be canonical isomorphisms. So we have that triangulation of cubification is the identity, but also the triangulation of flat is the identity. So the way you should remember this is that whenever you start from a simplicial set and you go to cubical set, either using blue or using red, and then you triangulate back, you find again the simplicial set you had started with. And if you have in mind any other category of cubes that has the same properties, 99% of what I say today will go through as well, because really this is all that I will use. Questions so far? Okay, so then let's go on to the construction of the model structures. So I'm repeating for you my first goal. So I want to argue that the left transferred model structure, which is the one where weak equivalences and cofibrations are created by the triangulation functor, exists. And I also want to argue that the right transfer model structure, in which weak equivalences and fibrations are created by T, also exists. And it is often the case that when you want to argue that the transfer model structure exists, you end up having to confront an acyclicity condition. And there are criteria in the literature that may help you guarantee that the acyclicity condition in your specific situation holds. So this tool, in the two examples that we're analyzing today, comes on the one side from the paper by Heske, Jorek, Riel, and Shipley, and on the other side by a classical fact that I believe is due to Kahn. So let's see what it says. It will be enough to assert that the left transfer model structure exists if we were able to show the following. Given a cubical set Y, we want to be able to produce a factorization of the folding map from two copies of Y into Y through this new object that we are calling cylinder of Y. And the requirement is that when I apply the triangulation functor to this factorization, what I obtain should be now, of course, in simplicial sets where I do have a model structure, and the requirement is that the first leg should be a cofibration and the second leg should be a weak equivalence. Okay, so this is what we will check in a moment. But first, let me tell you what goes to the right side of this box. So we will be able to say that the right transfer model structure exists. So here it's even easier. It would be enough if we convinced ourselves that T preserves all filtered colimits and that T composite flat sends all generating acyclic cofibrations to acyclic cofibrations. So let's see why these two.
Martina?
Yes.
This is Muriel speaking.
Yes.
On your right, is it, I mean, do you have also kind of same argument with the existence of a path?
Yes, so the
object.
I could have written the dual of what is on the left, and I think that the dual actually came first, but I'm not quite sure how to apply the dual of what is on the left side to this specific situation. Like it may hold, but the conditions that I have selected are easier to check in this case. But there is also a dual statement, yes.
Thank you.
So there, I think you would replace, like the cylinder would be more like a path object.
Yeah, yeah, exactly.
Yeah. So I believe that the inspiration to come up with this criterion was the classical, like dual one. But Emily can say more if not. Okay. So the proof fits in this box. It's just a couple of lines. Let's see, I want to argue that I can find the cylinder object and I'm defining it for you. So I say that the cylinder of Y is going to be the product of Y with the cubification of J, and J is the nerve of the walking isomorphism. So this was in Brandon's slides and it was called E1. It's the same guy. So what happens when I apply T to this newly defined cylinder? By definition, I have the triangulation of this product, but I know that T preserves products, so I'm obtaining T of the cubification of J times the triangulation of Y. And I also know that the triangulation kills the cubification. So this is just the usual cylinder in simplicial set that you would take of the triangulation of Y. And once you have recognized it for what it is, it's also easy to check that the extra conditions are verified. So we start with two copies of the triangulation of Y. We go to the cylinder of the triangulation of Y. This is naturally a cofibration. And when we project down to the triangulation of Y, this is the weak equivalence. So done. And the right-hand side is even easier because we already know that T is a left adjoint. So we know it preserves all colimits. This is really an overkill. And we also know that T composite flat is isomorphic to the identity. So in particular, it will send all acyclic cofibrations to acyclic cofibrations. And we're done. So we know that the model structures exist. And now let's go towards the Quillen equivalences. Before worrying about Quillen equivalences, maybe I am concerned about Quillen pairs to start with. However, this comes for free whenever I build a model structure by transferring an existing model structure. So for instance, by construction, T will preserve cofibrations and weak equivalencies in the red picture. So it is by construction equivalent pair. And dually, in the blue picture, T by definition will respect fibrations and weak equivalencies. So we do have equivalent pair also for free. And in order to prove the equivalent equivalence, again, we evoke a tool from model category theory. So this time it will actually be dual statements. So if we are in a situation where we have equivalent pair and we know that the left adjoint creates weak equivalencies, so this is not always true, but it is true in our situation, then in order to prove that it's equivalent equivalence, all I need to do is to check that the co-unit of any fibrant object is a weak equivalence. Now the dual statement is about to appear. If I am in equivalent pair where I know that the right adjoint creates weak equivalencies, then I just need to look at the unit of cofibrant objects. Okay, and once we have digested this model categorical proposition, then I can claim for you that T actually is part of a equivalent equivalence. In the red part, it's left equivalent, and in the blue part, it's right equivalent. So why? Well, I need to stare for some time at the co-unit of whatever object, but we have already mentioned that the co-unit of any object is the by now familiar isomorphism. And same thing happens on this side. I stare at the unit of this adjunction for any simplicial set, and it's going to be an isomorphism. So everything really seems like an overkill, but it just works. Okay, so we have these equivalent equivalencies. They were quite easy to accomplish, I guess. But let's have a look at what's going on inside them. And I don't know, let's try to get a feel, because by now we have built them, but I don't think that we have, I don't think that I have helped you develop any intuition for any of the two model categories. So let's see. What can I say about cofibrations in both of them? So on the one side, I like in the red part of the story, I can prove that any monomorphism is a cofibration. So this follows from the fact that triangulation preserves monomorphisms. And for instance, if you want a concrete one to have in mind, you can apply flat to the boundary inclusion of a simplex, and this is going to be a cofibration. But you can also build more exotic things. So here I'm taking two cubes and I'm gluing them over flat of the triangulation of the cube. And then I have a sort of folding map that folds it back to the two cube. So this one maybe looks very complicated, but when I apply triangulation, since triangulation commutes with push outs, really what I obtain is an isomorphism. So this is a cofibration. And it's not a monomorphism because by design, I have two cubes that are mapped to the same one. So monomorphisms are strictly smaller than cofibrations here. Any object is cofibrant. Who knows how to generate the cofibration? So this is definitely the main drawback of this setup. Now let's look to the other side. It's kind of an opposite situation. So there you can prove that any cofibration is a monomorphism. So for instance, just to have one in mind, we can recycle the previous one, flat of the boundary inclusion. And actually, these are all the generating cofibrations. So they are the building blocks of all of them. So in this case, they are explicit. The problem is that they don't generate very much. Like there are very few cofibrations in this model structure. So for instance, here's an innocent monomorphism. You can prove that it's a monomorphism, but I think it's not a cofibration. And I also think that the representable 2 cube is not cofibrant. Okay, so we have that these cofibrations are on one side more than monomorphisms and on one side less. Now, what can we say about acyclic cofibrations? And if we understand acyclic cofibrations, maybe we have a chance to also get a feel for fibrant objects. So if I apply flat to a Horn inclusion, it should be an inner Horn inclusion if I'm thinking about infinity 1, then this is going to be an acyclic cofibration, because when I apply triangulation, I'm just getting back the the Horn inclusion in simplicial sets. And here's another acyclic cofibration, the inclusion of flat of the triangulation of the cube into the cube. And here's another one, this kind of folding map that we had before. It looks complicated, but when, like, to both of these maps, when I apply triangulation, I'm getting back an isomorphism. So they are acyclic cofibrations. On this side, there's not much that I can say. I can reuse flat of Horn inclusions, but kind of, that's it. I don't know much more. Okay, now let's try to use these guys, like these remarks, to maybe guess and say something about fibrant objects. So if we stare at these three classes for a long time, what they are telling us, if you play like transposing lifting problems, are, first of all, that, okay, no, that's a comment 0. We already know that cubification is a right Quillen functor. So if I started with a fibrant simplicial set, then the cubification is going to be fibrant. Okay. And now I want to use the 3 classes of acyclic cofibrations that I have identified a moment ago to try and say as much as I can of fibrant objects. So the first one, if I write down the lifting problem, says that whenever Y is a fibrant cubical set, then the triangulation is a fibrant simplicial set. So this translates precisely having the lifting property with respect to this map. The second one kind of says that whenever I see this guy into my Y, I can lift to a cube. And this one kind of says that whenever I see potentially 2 cubes filling the weird guy, then they agree. So maybe a way to rephrase what I said a moment ago is that in Y, there is a unique cube whenever I see a copy of flat of triangulation of cube. And I have not checked the details, but I think that this is actually a full characterization. So I am quite convinced that Y is going to be fibrant if and only if it's the cubification of its triangulation and the triangulation is fibrant. So if this is true, what this means is that the fibrant objects are precisely, like the category of fibrant objects is precisely the category of fibrant simplicial sets, like isomorphism. Okay.
Martina?
Yes.
I have another question.
Mm-hmm.
That doesn't depend on the model category structure you take on simplicial sets? I mean, is it case for groupoids or for...
It works for both.
Category?
So there's a parameter epsilon that you can choose at any time, and the dependency of epsilon is encoded in this fibrant here.
Yeah, I know. I thought about the acyclic, maybe.
Yeah, so here, if you're thinking about infinity 0, then these guys are going to be all Horn inclusions. And if you're thinking about infinity 1, then you should add that K is not 0 and not N. Yes.
Okay.
And I guess these two don't depend on infinity 0 or infinity 1.
Okay, thank you.
Yeah. Okay, and on this side instead, again, if you play transposing lifting problems, what you obtain is that Y is fibrant if and only if the triangulation is fibrant. So there's a lot of fibrant stuff. For instance, in infinity 1 categories, the cubes are fibrant, but there's also this weird guy, which is fibrant. Just because when you apply T, you're getting just the triangulation of you're just getting delta 1 to the power 2. So this is a lot of information, and I'm not expecting you to retain all of it, but maybe the message that we could focus on is that in the left side, the main flaw is that we have no idea on how to generate cofibrations. We have the feeling that maybe there are too many of them, and we have the feeling that maybe there are too few fibrant objects, like we are kind of just reproducing simplicial sets. Then we might as well just work with simplicial sets directly. We are not really capturing the nature of cubical sets. And instead on the right-hand side, we have very few cofibrations. Like, yes, we can generate them, but there are very few and kind of too many fibrant objects. Like, again, we are kind of completely ignoring the structure of cubical sets. And whenever we have a question, we are just pushing it to simplicial set, answering there and then coming back. We usually start with the biased viewpoint of wanting the monomorphisms as cofibrations in our model category. So there is at least a way to solve that. So we can kind of interpolate between these two model structures, obtaining what I'm calling the intermediate model structure, for lack of a better name, in which we have the same weak equivalencies, but now the cofibrations are the monomorphisms. So the starting point for this slide is the observation that the two model structures that we've been analyzing have the same weak equivalencies, but one has too many cofibrations and one has too few. So here's a belief, which is not a theorem because again, I have not really checked it, but it seems like everything goes through. So I think that there exists a cofibrant generative model structure that I'm decorating with an M because it's like in the middle, in which the cofibrations are indeed the monomorphisms and the weak equivalencies are still created by triangulation. So if this goes through, then belief 2 is even easier to believe. Then T is going to be part of Quillen equivalence. It's going to be the left Quillen functor of Quillen equivalence. So let me just argue why I think that belief 1 may be a theorem. So normally in this situation, what you would do would be to try and apply Jeff-Smith theorem. And when you want to use Smith theorem, then you need to agree on what is the class of cofibrations and the class of weak equivalencies of the wannabe model structure that you're trying to build. And for us, they are already written in the statement. So the wannabe weak equivalence on cubical sets that I would like to have are those that are sent by triangulation to weak equivalencies of simplicial sets. And that's my schematic way of denoting it. And the class of wannabe cofibrations are the monomorphisms. Now, if you pull out the NLab page of Jeff-Smith theorem, there's a long list of things that you need to check, but some of them either are for free or are just like kind of straightforward, and there are really two things that you need to sit down and convince yourself of. So let me comment on these two non-straightforward things. So the first thing that I need to check is that if I take something that is a wannabe cofibration and a wannabe weak equivalence, that the class of wannabe cofibrations that are also wannabe weak equivalencies is closed under push out and transfinite composition. So to do this, I'm going to stare at any push out or transfinite composition of things that are in there. And since I'm trying to prove that it's in the intersection, I need to convince you that it's in C and that it's in W. So okay, that's not a very deep mathematical statement, but by splitting the problem in two, it becomes easier to see why they should be true. So if we just focus on the cofibration part, I think you can argue something along the lines of this class is closed under push out or transfinite composition before you intersect it with W. So in particular, if the inputs I have are in W, I can just disregard this information, but I know that the result will still be a wannabe cofibration. And instead, to argue that push out or transfinite composition is a wannabe weak equivalence, this I need to work slightly more. It will take 2 lines instead of 0 lines. So I'm going to observe once again that triangulation preserves colimits. And I'm going to observe that if I take the triangulation of something that is a wannabe cofibration and a wannabe weak equivalence, I'm going to land in something that is an acyclic cofibration in simplicial sets. So now if I put together these two ingredients, if I'm looking at say the transfinite composition of things that are in C intersection W, and I want to know whether this is a weak equivalence, I need to apply T and answer this question in simplicial sets. But if I apply T, I can commute T with push out or transfinite composition. And there I find myself with the push out or transfinite composition of acyclic cofibrations in simplicial sets. And I know that this is going to be still an acyclic cofibration, so in particular a weak equivalence. Of course, I could write a much longer proof, but it's the type of reasoning where you just sit down and put together all the pieces. And I think it should work. So that's one non-straightforward condition that needs to be met to apply the NLab Jeff-Smith theorem. And the second one is you need to check that if you take something that has the right lifting property with respect to the wannabe cofibration, it's a wannabe weak equivalence. So again, how do I check something like this? I need to start with something that has this right lifting property. I need to apply T and check that I have a weak equivalence in simplicial sets. So let's see. So I apply T to something that has the right lifting property with respect to cofibrations. And if you write down what it means, and if you use the fact that flat respect cofibrations, which I have mentioned before, you obtain that the triangulation of something that has this right lifting property is something that has the right lifting property with respect to cofibrations, but now in simplicial sets. And in simplicial sets, I already know that something that has the right lifting property with respect to cofibrations is an acyclic fibration. So in particular, a weak equivalence. And since I have shown that the triangulation of something is a weak equivalence, what this means is that the thing I have started with, which was inside the brackets, is mapped by triangulation to a weak equivalence. And so it is a wannabe weak equivalence in the category of cubical sets. So I think that this is fine.
So Martina,
yes.
I have some supporting evidence for all of this. So I just copied into the, so there's a mixing model structure theorem that's due to Rick Jardine. I just copied an NLab page into the chat. But what I'm pretty sure the hypotheses are is firstly, you need two model structures, like your red one and your blue one, and you need them to have the same weak equivalences. And then you need to have a weak factorization system whose left class sits between the two left classes. So if you take mono trivial fibration for that weak factorization system, then I think you're good. And the proof is exactly like you've just sketched. It's basically Jeff-Smith's theorem.
Okay, thanks. But I thought I had checked these intermediate models. No, what is it called? Is it called mixed? And I thought it didn't apply. Maybe I didn't.
Right, so mixed is a different one. So the mixed one is much better known. And that's due to Cole, or I can't remember.
Okay. I think that's the one I checked and it didn't apply, but it's good to know that.
You're right.
Yeah, and it does feel
this
like
is a weird one.
It does feel like here I'm really not using anything. Like one could follow this talk without knowing anything about cubical sets, really.
Right. Yeah, totally. So.
And even if you don't believe my sketched argument here, another maybe supporting evidence of this is that if you think about what this should give for epsilon equals 0, I think you should agree with the test Grothendieck model structure. The only thing that I'm not sure about is that for the test model structure, you need to go to spaces. And I'm assuming that to go to spaces, you go through simplicial sets using the triangulation. So I would think that when epsilon is 0, in any case, this agrees with the test model structure. And so in that case, we already know that it should exist. Okay, so the conclusion is that we have now 3 model structures that are, like, we at least understand well the relation between each other, and they all have the correct homotopy theory. Depending on what's your goal, you may be able to move from one to the other. Okay, so they all live in one connected component of homotopy theory, but there was another model structure on cubical sets that was mentioned yesterday in Emily's talk, and it's the one related to homotopy type theory, and I just wanted to give a few comments on how this fits into the picture, or rather does not fit. A lot of it, Emily already said it yesterday. So there is this model structure due to Christian Sattler in which, so it's on the same category of cubical sets, and I'm decorating it with this hot. So the monomorphisms are the cofibrations, and the acyclic cofibrations are generated by a certain class, and as Emily said yesterday, we should think of them as all the possible cubical like open box inclusions. So they are push out products of the inclusion of the 0 cube into the 1 cube and the generic monomorphism. So really these, like some features of this model structure is that I think maybe the original motivation was that this model structure gives a cubical model of homotopy type theory, and it satisfies axioms that homotopy type theorists care about and that I ignore, but I think the univalence axiom was one of them. And it also can be done for many categories of cubical sets. I think Emily yesterday mentioned the one that also has reversals, as well as the one that we're looking at today, and also things with without connections maybe, but you can do it with many of them. And it also has a constructive side because actually it's an algebraic model structure. So it's favorable if you're trying to implement like constructive logic. And Emily also told us that arguments of Buchholz and Sattler, like they provide counterexamples so that we know that for different cube categories than the one that I'm considering today, it is already known that the homotopy theoretic model structure does not model infinity groupoids. So it's something else. And what happens if we are just looking at our model structure? Like, is it known whether it models infinity groupoids? And maybe the question can be rephrased as, what is our understanding of fibrant objects in this model category? And I think the answer at the moment is that we just don't understand fibrant objects. And the main obstacle, once again, is that even though we know that there is a set of generators for monomorphisms, they are not pretty and they are kind of not explicit. So with Emily, what we thought was that we had actually found a nice small list of generators for the class of monomorphisms. And based on that wrong assertion, we were then able to fully characterize also a set of generating acyclic cofibrations, and then also a nice and pretty description of fibrant objects, but it doesn't work. So at the moment, the main obstacle is unfolding or like finding a nice set of generators for monomorphisms. And in any case, it's quite straightforward to check that triangulation is equivalent pair. Like, for instance, you may argue that you already know that triangulation respects monomorphisms. And if you apply triangulation to this open box inclusion, you already know that it commutes with products and push-outs, and you can check that it goes to a push-out product of a cofibration and an acyclic cofibration in simplicial sets, and so it's going to be an acyclic cofibration. So this is like really on the easy side, but as Emily said yesterday, it's an open problem and probably really hard to understand whether the homotopy theory is the same as infinity groupoids or it's something else, and if it's something else, who knows what it is. Yeah, and I'll stop, take questions.
Okay, thank you very much. So please join me in thanking Martina for this talk. And yeah, we'll open the floor for questions and comments.
So your green model structure and which I think should be purple, by the way, because it's like mixing red and blue, but otherwise I thought the slides were beautiful. So your green model structure has the same cofibrations as the Sattler model structure. Do you know anything about a comparison between them? Like, can you say?
I think it's essentially the same as comparing it with simplicial sets.
I guess what I mean is, do you know any, like, a direction of, so certainly proving that they were equivalent would be equivalent to proving it's equivalent, but like, do you know anything about, is there a equivalent pair in one direction or the other?
So the feeling, so if something is a Sattler acyclic cofibration, then it's also a mixed model structure acyclic cofibration. And the reason is that the cofibrations are the same, and to know whether it's a weak equivalence or not, you need to apply T. And when you apply T, it is a weak equivalence. So I think that the identity from Sattler to mixed is left Quillen.
Right, so then your mixed fibrations would tell you some of the fibrations, I guess, in the Sattler model structure, but maybe not all of them. And that's kind of the question you were
like my intuition is that, so assuming that my characterization of fibrant objects, no, okay, I was gonna say something with the red one, but okay, let me say something that doesn't quite fit, but in the red model structure, the fibrant objects, I think, as I said, are essentially really like simplicial sets. They are cubifications of fibrant simplicial sets. So whenever I see these, what we used to call the triangulated skeleton of a cube, namely flat of the triangulation of a cube, there is really a unique cube to fill it. And I find this unnatural. I would expect more something like there is a cube, but it's unique up to some higher homotopy. And I don't know, I would expect that a good notion of a fibrant object would be something that has the same flavoring properties, but not with this super strict uniqueness. But this is not a precise statement.
Yeah, I mean, it'd be cool if you could like use these model structures to kind of squeeze the Sattler one somehow. And I mean, that's not a very precise idea, but I think you know what I mean.
But while I was preparing the talk, I went back to all the things that went wrong in the thing that we were writing last year. And like at least 5 times I was like, maybe this can work, and then it never does. So I kind of convinced myself that we cannot solve a hard problem just with this like straightforward 2 lines proof, but it would be cool, yes.
Okay. Any other questions? Okay, maybe I'll ask a quick question if that's okay. So, well, I'll start with a comment, and maybe someone can correct me in case I get something wrong. So my impression was that in the case of the minimal cubical sets, so just spaces and degeneracies, Trzynski actually shows that the Grothendieck model structure is the one generated by, is the one left induced by T. So monomorphisms are, yeah, and then weak equivalence is. So it seems to me, I don't exactly remember how you said it. Your mixed model structure is related to the test category. It seems to me that it may be exactly the test category.
I think that the mixed model structure is the test category when epsilon is 0.
Right. Yeah. Yeah. Okay. Because because the test category model structure is like Jeph-Smith's theorem, like in the abstract somehow. So it seems like
the only difference is that my models, like the green model structure, is testing weak equivalences in simplicial sets, whereas the test model structure is testing in spaces. But I'm assuming that there's a commutative diagram. And
right.
You see what I mean?
In Trzynski, I know. Yeah, like that you go to spaces because.
Like I imagine that in the test model structure, the usual functor to spaces factors as triangulation to simplicial sets and then the realization from simplicial sets to spaces.
So I think it's isn't it something like cubical sets you go to cat by taking the category of elements of the cubical set, and then you go to simplicial sets by the nerve functor, and then you go to spaces.
And is this first composite the triangulation? Going to cut and then to simplicial
I think
sets?
compares it to triangulation in his thesis, and he shows that there's the natural weak equivalence, and that's how he shows that the model structure can be equivalently created by triangulation.
Yeah, I see. So that this is all we need.
But
I think that this is all we need then to say that it will be the test. Yes.
Yeah. So I think maybe this statement can be. Okay, but I think that's pretty cool because like we understand now the test category model structure slightly better. I don't think I knew everything that like you said about this. So and like the whole problem is comparing test to Sattler. So I think just like Emily said, I think I'm now arriving at your chain of thought, and we can
Like,
squeeze the.
What we thought was the following. So here are evident generating monomorphisms. There is the flat of the boundary inclusion, and there is the map from flat of the triangulation of the cube to the cube. So if you're thinking as with your like Schiff intuition, I think this is like saying whenever there's room to build a cube, you can build a cube. And we thought that these were all, I think, but they are not. And there's a subtle mistake that was extremely annoying, but yeah, it doesn't work. So you can still use these and to say like, I'm generating some subset of monomorphisms, but it's not going to be all.
So there's there's a potential application of Martina's model structure in the case E equals 1. And I guess I'm thinking of the green one in particular, which is, so remember that's the one where the triangulation, so the cofibrations are the monomorphisms and the triangulation creates the weak equivalences. And so as you can check that this is a monoidal, Cartesian monoidal model structure, because the SM7 axioms is something about push-out products of monomorphisms, which I think is always true. And then the other thing is like created by T or something. T preserves these push-out product diagrams. And T also preserves products because it's secretly a right adjoint as well. And so what that means is you can take anything that's enriched over the Joyal model structure on simplicial sets and re-enrich it over Martina's cubical model structure. So if you wanted to
by
redefine,
using like, doesn't it go the opposite way?
So you're changing the Homs using the right adjoint to T.
Okay.
So if you had a quasi-categorically enriched thing, it becomes a cubically enriched thing by applying C to the Homs. But it's also tensored and co-tensored. So this is like the best way to change base between enriched model categories. And so the consequence is that if you wanted to redefine the notion of an infinity cosmos to be something that was like enriched over cubical sets as opposed to over simplicial sets, this would be a way to do that.
Yeah, I see. Cool. It's a pity that the good properties of this category of cubes and the good properties of the other categories of cubes are completely disjoint.
Yeah, we need a unified theory of cubes. I think we're not doing very well at progressing towards that. It's like every single pocket's a different cube. Yeah.
But like, what would drive me crazy is like, what if I need to remove one face, like just one? Like, it's so weird to work just with one connection. I don't know. So as far as you know, maybe you just need to pick a weird subset of things. Now, I know that like you explained where taking one connection comes from, but it still sounds odd to me. But.
Yeah, but maybe the other thing is, so I think like if you do infinity groupoids, if you have one connection, then your concomplexes will have the other connection, just using some liftings.
Right.
So I think that kind of like you kind of get it, but maybe I'll say one other thing. So the cubification thing, like that, I think there's some potential there. So there's another functor from cubical sets to simplicial sets. I think. Wait, let me think about it. No, so cubification will be simplicial sets to cubical sets. Sorry. So I need to tell you where to send simplices. It will be a left adjoint. Just like triangulation is a left adjoint. So I only need to tell you where to send the simplices. And I'm going to send it to simplex, let's say. So I'm going to take the 3 cube, and I'm going to remove the initial vertex. So I'm also removing 3 faces adjacent to the zero vertex, and so I'm getting like those.
This is like a subdivision or something.
So this is the subdivision.
Exactly.
Yes.
Exactly. That's exactly subdivision. And if you want to make it even more precise, when you start with an n simplex and you apply cubification that I described, and then triangulation, you get subdivision. And so now the question is, what happens if you start with a cube, you triangulate it, and then you cubify it? And yeah, we had this idea of using it as like a replacement for X infinity, but somehow it didn't work. Tim found a much nicer solution. But it seems like at least that would give you like 2 left adjoints that again you can try to do something with.
Yeah, I see. It's cool, but I don't know what the answer is.
Yeah, I don't know. But I think in order for cubification to define a co-cubical object, I think again you'll need like a connection, like one connection or something. is one of those things that, yeah.
But in any case, now you're developing all the theory for the ones with one connection, so I think we should just stick to that one.
Well, except Yuki insisted on in the comical paper on including the other connection. So.
Okay. It makes me feel a bit better, I must say. But yeah, I'm obsessed with symmetry in general. So. Okay.
Okay, so do we have any further questions or comments? Okay, if not, then let's thank Martina again for the talk. And yeah, thanks.